Mitchell Lee, and today Philip and I are going to tell you about technical developments in classic Sudoku. So I'm going to start by telling you about something called Fractional Sudoku, which is a Sudoku variant in a very loose sense of the term. Unlike many of the Sudoku variants that we all know and love, this one isn't really as amenable to actually setting and solving puzzles. However, it has a great deal of theoretical interest. So first I'm going to start by explaining the rules of fractional Sudoku. So let's talk about what Sudoku is. This probably isn't necessary for this particular audience, but I want to briefly review them just so that we can contrast them to the rules of fractional Sudoku that we're about to see. So Sudoku is a puzzle played in a 9x9 square grid, divided into 9 3x3 boxes. And a Sudoku grid is a way of writing digits, which just means the symbols 1 through 9, into cells, such that each cell of the grid contains exactly one digit, and each row, column, and outline 3x3 box contains each of the digits exactly once. So here's an example of a Sudoku grid, and here I'm just talking about the finished Sudoku grid, so I'm not talking about Sudoku puzzles yet. We're just considering finished grids. And all the examples in this video are from SudokuWiki.org. All right. So that's very familiar to us, I hope. Now let's introduce a little twist to this. Okay, so I'm going to give you the rules of fractional Sudoku, and they might seem a little confusing at first, but I hope that with a few examples, things will become more clear. So a fractional Sudoku grid is a way of writing parts of digits, which are again the symbols 1 through 9, into the cells of the same 9x9 grid, such that each cell of the grid contains exactly one digit in total, and each row, column, and 3x3 box contains each of the digits 1 through 9 exactly once in total. And I'm going to call ordinary Sudoku integral Sudoku to distinguish it from fractional Sudoku. So again, this might be a little unclear. We're going to see some examples. I'm going to show you some examples of 4x4 fractional Sudoku grids. 4x4 fractional Sudoku works just the same as 9x9 fractional Sudoku, but we're using the digits 1 through 4 instead of the digits 1 through 9. So here is an example of a fractional Sudoku grid, and what I want you to notice is that whereas in an integral Sudoku grid, every cell would be filled by just one digit, if you look, for example, at row 2, column 3 here, it's actually being shared by two digits, 1 and 3, with 1 taking up 2/3 of row 2 and column 3, and 3 taking up 1/3 of row 2, column 3. Or in other words, I might say at some point during this presentation something like row 2, column 3 contains 2/3 of a 1 and 1/3 of a 3. Throughout this talk, I want you to ignore the numerical values of the digits and treat them merely as symbols. So for example, if I say that row 2, column 3 contains 1/3 of a 3, that's not the same as it containing a 1. 1/3 of a 3 is not the same thing as a 1. All right, so even though a lot of these cells are being shared by more than one digit, you can see that all the rules of Sudoku are still satisfied. For example, if we look at row 2 of this grid, it's still got exactly 1, 1. It's just that 1/3 of that 1 is in row 2, column 1, and 2/3 of that 1 is in row 2, column 3. So the 1 is sort of split across two cells, but every row, column, and 3x3 box still contains exactly 1, 1, exactly 1, 2, exactly 1, 3, and exactly 1, 4. All right, are we good with that? Yeah. Okay, let's look at another example. This is an example of a fractional Sudoku grid that just comes from taking an integral Sudoku grid and filling each cell with a complete digit. So this still counts as being a fractional Sudoku grid. And we'll see one more example, which is this one. Here I filled every single cell of the grid with 1/4 of a 1, 1/4 of a 2, 1/4 of a 3, and 1/4 of a 4. And you can check that all of the rules of Sudoku are still being satisfied here. Okay. Now, I should say, all right, sorry. I should talk about this. one important operation that you can do with fractional Sudoku grids is to mix them. So for example, I have two fractional Sudoku grids here, and I've mixed them half and half. And what that means is that in each coordinate, so for example, in row 3, column 3, the first grid contains a 2, and the second grid contains a 3. So in the mixed grid, row 3, column 3 is going to contain half of a 2 and half of a 3. So we've just mixed them. And by mixing fractional Sudoku grids in this way, you can make infinitely many. So there are actually infinitely many possible fractional Sudoku grids. All right. Now, Sudoku, we're not all here because we like staring at finished Sudoku grids. We're here because we enjoy actually solving puzzles. And you can do fractional Sudoku puzzles as well. So I've put an example here. So it just works like an integral Sudoku puzzle. Some of the cells are already filled, and you have to figure out how to fill the remaining cells. So this is a very simple example. I've already placed in all the copies of all the digits except 1 and 2. So 3, 4, 5, 6, 7, 8, and 9 are already in there. But now we need to fill the remaining 8 cells with the digits 1 and 2. Now if this were an integral Sudoku puzzle, this would have no solution. Because you would have a pentagon of cells that can only be filled with 1 and 2. This is what is known as a bi-value autogon. That's not possible. However, if we think of this as a fractional Sudoku puzzle, it actually has a unique solution, which is to have the digits 1 and 2 share each of the remaining 8 cells half and half. So this is the unique solution to the fractional Sudoku puzzle. If you need to sit down and try to convince yourself of that, you can take some time to do so. Okay. Another really good source of fractional Sudoku puzzles is taking any integral Sudoku puzzle and just interpreting it as a fractional Sudoku puzzle by putting the same givens in the same position. So I've taken a puzzle from Sudoku Wiki, and here we're interpreting it as a fractional Sudoku puzzle. And we can ask, does the puzzle still have a unique solution? Now we know that the fractional Sudoku puzzle on this slide must have exactly one solution, or at least one solution, rather, because the integral Sudoku puzzle has one solution. However, is that the only one? And in this case, it actually is the only solution, and we can prove it by solving this puzzle logically. So using the rules of fractional Sudoku, we're going to solve this puzzle without doing any guessing, and we're going to prove that the solution that we just found is the only one. And this might seem like a daunting task, but actually solving a fractional Sudoku puzzle like this works very similarly to solving an integral Sudoku puzzle. And one first step that might jump out at you is trying to place the 7s in box 5, right? So we start with the 7s in box 5. And what you can notice is that because of the given 7s in the grid, there can't be any part of a 7 in any of the 4 cells that's marked with an X. So all of those 4 cells have to have no 7 in them at all. However, we know that in box 5 there has to be at least a total of 1 7, which means that the cell in the center of the grid has to contain a complete 7. It's not shared. So this technique that we've just used is called a hidden single, and what I've essentially just shown you is that you can use hidden singles in fractional Sudoku just as well as you can in integral Sudoku. And you can use the same technique to place a 3 in row 4, column 3. Again, there can't be any part of a 3 in any of the cells marked with an X, so the 3 in box 4 has to be in row 4, column 3. The same technique works in rows and columns, so you can do singles in rows and columns as well. Once you do enough hidden singles, you eventually reach this position to the left. And from here, it's impossible to make any more progress with hidden singles alone. However, there's some other techniques that we can use. I'm wondering, does anyone spot what we can do next here? Yes?
What stops
So nothing in the rules of fractional Sudoku would stop you from doing that. So I could put half of a 2 in this cell and half of a 2 in this cell. But we will see by logically solving the rest of the puzzle that that's not what the finished grid will look like.
Would that be a pencil mark?
You can make pencil marks in fractional Sudoku, and we're actually going to see some examples of that later in this solve. If this were just an integral Sudoku puzzle, how would you proceed here? Maybe it's a little bit hard to see, and I should, yes?
I don't see one, but I'm assuming you're looking for a naked single.
Yeah, there's a naked single here. Yes?
1 and row 4, column 4?
Yeah, so let's look at row 4, column 4. Great, thank you. And we're going to consider the contents of this cell. Now remember, the rules of fractional Sudoku say that every cell has to contain exactly 1 digit in total, right? Now that one digit can be made up of a bunch of different parts. But let's consider the contents of row 4, column 4. Because of the 2 that we've already placed, there can't be any part of a 2 in row 4, column 4. Similarly, there can't be any part of a 3, 4, 5, 6, 7, or 8. But we need to fill that cell with some digit. So the only possibility is that we fill it with a whole 1. So this is a naked single, and this is valid in fractional Sudoku as well. So using some more singles, we can reach the position to the left, and here's where we're going to start to do some sort of pencil marks, okay? And I'll explain to you what they mean, because they mean something a little different in fractional Sudoku. Let's consider these specific 3 cells, and the reason for this will become clear. And we're going to mark candidates in these 3 cells. So let's start with row 2, column 2. We see that it sees an entire 2, a 1, a 4, a 5, a 6, a 7, and 9, which means that the digits that it doesn't see are 3 and 8. Okay, and we're going to mark 3 and 8 in the center of this cell. Now note that in integral Sudoku, when I mark 3, 8 in the center of a cell, that means that cell either has to contain a 3 or it has to contain an 8. That's not what this pencil mark means. This pencil mark means that either the cell contains a 3, or it contains an 8, or it contains some mixture of a 3 and an 8. We haven't ruled out the third possibility yet. And then using a similar method, we can mark candidates in the other 2 highlighted cells. So let's leave these alone for now, and let's look elsewhere. Anyone see anything interesting here? It has to do with the digit 7 and its placement in this grid.
Are we looking at columns 3 and 7 then? Because there's the 1, 7 in row 7, and then in boxes 1 and 3, you have the 7s down the column. Is that what we're...
So it does have to do with column 3 and column 7, yes. Yeah, and rows 3 and 7. So there's an X-wing here. So let's consider the possible locations for the 7 in rows 3 and 7, right? And also consider, yeah. So let's think about the logic here very carefully to make sure we're not making a mistake, because things get kind of thorny in fractional Sudoku. So in row 3, there are 2 highlighted cells. And we know that those 2 highlighted cells have to have a total of 1, 7 in them, right? We don't know yet that the 7 has to go completely in one of these 2 highlighted cells in row 3. It could be split between them, but we know that these 2 highlighted cells have to have a total of 1, 7. Similarly, in the 2 highlighted cells in row 7, there again has to be a total of 1, 7. Okay? But that exhausts all the possibilities for a 7 in columns 3 and 7. That's what an X-wing does. Thus eliminating the possibility of a 7 in any of the cells marked with an X. Okay, so using that we can update our pencil marks, and we end up with, I hope this one's a bit more clear what we're about to do. There's only one step left other than singles, which is to notice that there's now a 3-8 pair here, right? So again, the logic is a little different from how it is in integral Sudoku, but it still works. The idea is that these two cells, these two circled cells, have to contain each exactly one digit. However, that digit that they contain has to be some mixture of 3 and 8, and that accounts for both of the 3s and 8s in the row, which means we can eliminate 8 from row 2, column 3. Placing a 4 there, and from here, we can just solve the rest of the puzzle. Okay, this is exactly the solution that I showed you on an earlier slide, so why did I go through all the trouble of solving the puzzle when we already knew the solution? Well, that's because now we know that the puzzle can be solved logically, and thus that it has a unique solution. So let's go back and think about all the techniques that we used to solve that puzzle. We used hidden singles, naked singles, X-wings, and naked pairs. And what I wanted to show you with that puzzle is that all of these techniques work just as well in fractional Sudoku as they do in integral Sudoku. So I'm going to call them fractionally valid. Some people call these techniques rank 0. They're the same thing. Okay. So now one might ask, if I take, sorry, before we get there, let's talk about some more fractionally valid techniques. There's some pretty interesting ones here. If you haven't seen these techniques before, don't worry. You can just read through the list. I think the most interesting one here is the multi-sector locked sets, also known as MSLS, and Philip will definitely be talking about MSLS and set, which is a different way of thinking about the same technique in his part of the talk. So, after seeing that puzzle, you might think that fractional Sudoku is the same thing as integral Sudoku. I mean, we just solve the puzzle the same way. Yes, we'll talk about that as well. But it's not. So here's an example of an integral Sudoku puzzle that has a unique solution. But when I translate it into a fractional Sudoku, it's not going to have a unique solution anymore. And this is something that I actually found in a Math Overflow post. So one solution to this puzzle, oh, did we? One solution to this puzzle comes from just taking the unique solution to the integral Sudoku puzzle and transferring it over. But here's another one, where some of the cells are being shared half and half between the digits. In fact, there are infinitely many solutions, and you can show that by mixing these two solutions with various ratios between 0 and 1. So what went wrong here? Why doesn't this puzzle work as well as the previous one? Well, let's first solve this integral Sudoku and talk about what techniques we use to solve it. So I think there are many approaches to this puzzle, but the most elementary way is to use simple coloring. So we're going to highlight the cells in these 4 boxes where a 2 can appear. And again, we're just doing this as an integral Sudoku puzzle. And we're going to color these highlighted cells blue and red with no 2 highlighted cells in the same row, column, or box having the same color. Right? So based on our coloring, we know that there are 2 possibilities for the location of the 2 in these 3 boxes. Either all the blue cells contain a 2 or all the red cells contain a 2. And therefore, these 2 circled cells, which see both a blue and a red cell, cannot contain a 2, thus letting us place the 2 in box 5, and from there we can solve the rest of the puzzle using singles. So that's how you solve this integral Sudoku puzzle. And now we have to ask ourselves, why doesn't the same logic work in fractional Sudoku? Well, we're still allowed to do the same red-blue coloring, except now, instead of 2 possibilities, there's essentially infinitely many, right? You can have all the blue cells containing a whole 2. You can have all the red cells containing a whole 2, or you could have some mixture of these possibilities. Like, for example, each of the blue and red cells containing half of a 2. And in this third case, you're not able to eliminate 2 from either of the circled cells. And by eliminate, I mean completely eliminate. You're not allowed to eliminate the possibility that there's a part of a 2 in these circled cells. So that's why the logic that we use to solve the integral Sudoku doesn't work on the fractional Sudoku here. And there are many other techniques that work in integral Sudoku but do not work in fractional Sudoku, and you can see the list here. Okay. All right, let's talk about this puzzle again, because we just talked about how this puzzle has infinitely many solutions, but now I'm going to ask, what are they? And of course, it's impossible to actually list them all. However, maybe what we can do is somehow visualize them. And in fact, we can, but before we can really do that, I need to put integral and fractional Sudoku on a more solid mathematical foundation. So I'm going to reframe the rules of Sudoku in a slightly different way for you, okay? Normally, when you see a Sudoku puzzle, it says fill each of these 81 cells with a number. But we can reframe this. We can think of a Sudoku grid as being made up of 729, which is 9 cubed numbers, all of them being 0 or 1. And the way that we do this is that for every value of R, every value of C, and every value of D between 1 and 9, we're going to find X, R, C, D as 1 if the digit in row R, column C is D, and 0 otherwise. So for example, if we look at this Sudoku grid, the cell in row 5, column 6 is a 2, so we would say that X562 is 1, whereas we would say X563, for example, would be 0. Okay, are we good with that? And then, using these variables, we can actually encode all of the rules of integral Sudoku. So the first rule of integral Sudoku is that each of these variables, X, R, C, D, is only allowed to be 0 or 1. And then we also have this rule that every cell in an integral Sudoku is only allowed to contain 1 digit, right? And what that means is that if you look at any row R and column C, and you look at the variables XRC1, XRC2, and so on up to XRC9, that means that exactly one of those has to be 1 or true, and all of the rest of them have to be false or 0. And you can encode that in this equation, XRC1 plus ... plus XRC9 equals 1. We also have a rule in Sudoku that every row has to contain each digit exactly once. And you can similarly encode that as an equation, like the one that you see here. We also have a rule that every column has to contain each digit exactly once, and you can encode that in an equation as well. And you'll probably notice that there's some symmetry between these three rules, and I think this symmetry has actually been used by a couple of setters in the past. And then, finally, we have a rule that every digit appears in every box exactly once. And that one's a little more complicated, but I've just written it here. Don't worry about if you don't understand what's going on there. And the above equations have to hold for all R, C, and D from 1 to 9, and I and J and 1, 4, 7. Okay. So every integral Sudoku grid has a corresponding 729 tuple of variables that satisfy all of these conditions. So every time you've solved a Sudoku in your life, you've really been solving these equations on the slide. All right, and now let's talk about how we can modify these to get the rules of fractional Sudoku. And actually, we only have to make one small modification. which is that instead of saying that XRCD has to be either 0 or 1, we allow it to be any number between 0 and 1. And we're thinking of XRCD now as the share of the digit D in row R, column C. So any fractional Sudoku grid is really a solution to these equations and inequalities that you see here. Okay. Now, I'm going to let P be the set of all solutions to the system of linear equations and inequalities on the previous slide. Oh, by the way, I should say the process that we just did, all we changed was that we changed the first rule about XRCD being 0 or 1, and let XRCD be anything between 0 and 1. That process is called fractional relaxation, and it can be applied to a wide array of problems, and one of the benefits of fractional relaxation is it makes problems easier to do using a computer. Let P be the set of all real number solutions to the system. This thing is called the Sudoku polytope, okay? This can be thought of as a subset of this giant 729-dimensional space, because every point in the Sudoku polytope is determined by these 729 variables. Okay, and every point of this Sudoku polytope P has a corresponding fractional Sudoku grid. All right, now this thing is really hard to visualize because it's living inside this 729-dimensional space. But one way we can visualize it is to look at various pieces of it, and that's actually what we're going to do later. But for now, I want to talk a little bit about what I mean by polytope. So a polytope, a convex polytope, is kind of a generalization of the kind of shapes that you see here, like the polygon and the polyhedron, except in any number of dimensions. Essentially, it's something that's made up of flat and straight pieces, and the line segment between any 2 points in the set is contained within the set. All right, so one misconception that I want to knock out straight away is saying that the Sudoku polytope is 729-dimensional, because it's not. It's living inside this 729-dimensional space, but you can have a triangle, for example, which is 2-dimensional, living inside the 3-dimensional space. So that doesn't necessarily mean that the Sudoku polytope is 729-dimensional, and in fact it's not, because many of these variables are redundant. So for example, once we know the fractional share of the digits 1 through 8 in a cell, we can deduce the share of the digit 9. And once we know the contents of 8 cells in a row, we can deduce the contents of the last cell in the row. And similarly for columns and boxes. So actually, in order to communicate an entire fractional Sudoku grid, I don't need to tell you every single one of those 729 numbers, because some of that information is redundant. In order to communicate a fractional Sudoku grid, I only need to tell you the shares of the digits 1 through 8 in these 60 cells. And what that means is that the dimension of the Sudoku polytope is actually 480 instead of 729, which I'm sure is a relief to all of you. So, still, this is well beyond what any of us can visualize. However, we can get a glimpse of the geometry of this Sudoku polytope by actually looking at Sudoku puzzles. So I want you to look at this fractional Sudoku puzzle and consider, and of course this does not have a unique solution at all. It has many, many solutions. It's only got 2 givens. But if we think about the set of all the solutions to this puzzle, what that is the set of all points in P that also satisfy these three equations, right? x158 has to be 1/2. x159 has to be 1/2. That's just saying that row 1, column 5 is shared half and half between the digits 8 and 9. And x473 has to be 1. That's just saying that row 4, column 7 contains the whole digit 3. And here's kind of a cartoon picture of what we're doing when we think about the set of solutions to this puzzle. We're taking the Sudoku polytope P and we're taking a slice of it. Now, this is not an accurate drawing because in reality the Sudoku polytope is 480 dimensional, but this is how this is how I want you to think of the solutions to any given fractional Sudoku puzzle. It's a cross-section of P. So every time we look at a fractional Sudoku puzzle, we're looking at a little slice of the Sudoku polytope. So for example, remember this fractional Sudoku puzzle from earlier? How we said it has infinitely many solutions? Well, the set of solutions actually forms a line segment. It has dimension 1. Yeah. So the two endpoints of the line segment represent the two extremal solutions to this fractional Sudoku puzzle. And every other point on the line segment represents some kind of mixture of those two extremal solutions. So that's what I mean when I say the set of all solutions to this puzzle is a line segment. And we say that this puzzle has fractional dimension 1 because the dimension of its solution set as a fractional Sudoku puzzle is 1. Here's another example of a fractional Sudoku puzzle. This one has a 2-dimensional solution set. And there are 4 extremal solutions to this puzzle. These are actually called vertices. And the general solution comes from mixing these 4. And there are some points inside the solution set of this puzzle that can be formed by mixing in 2 ways. And then you can get fractional Sudoku puzzles of dimensions 3, 4, and higher. And this is actually a pretty useful tool for analyzing classic Sudoku puzzles. So if I give you any classic Sudoku puzzle, I can ask you, what is the dimension of its solution set as a cross-section of the Sudoku polytope? If a puzzle has a unique fractional solution, then its fractional dimension is going to be 0 because its solution set is a point. And we've also seen puzzles with fractional dimensions 1, 2, and 3. And one of the things that Philip is going to talk about is how fractional dimension is one way of classifying how difficult a puzzle is. And it correlates quite strongly with previously defined measures of Sudoku difficulty. For example, the GSF-Q2 rating. And then I think that's essentially all I have. This last slide, I'm just showing you a bunch of puzzles and their fractional dimensions. So these are pretty well-known Sudoku puzzles. Interestingly, this puzzle, Tatooine Sunset by Philip Newman, even though this is quite a difficult puzzle, it has a fractional dimension of 0, and that's because it can be solved with set. The highest known fractional dimension of any valid classic Sudoku is 115, and that was also found by Philip. All right, and then we have a few more questions here, but I don't want to take up too much of your time. Thank you.